All right, welcome back to a lecture series by me. I'm Professor Wu. This is a course at Northeastern University, and today we're going to go over the first lecture on the foundation of kernel methods. Now, kernel methods is one of those things that uh, people talk about it, but very few people actually knows what's going on. Um, so, so we're going to go over the foundations so that you have a good idea. Make sure you understand the prerequisites, right? If you don't know the prerequisites, you want to be able to know them first before you watch this. And these are the various topics we're going to cover today. So let's get started. Now, a function, a function. If you've taken all the previous courses up to this point, it's not a surprise to you that a function can be viewed as a combination of functions. So let's look at a function of a line. So this is what we're used to seeing. This is a function of line, depending on how you set the value a and b. So 5x plus 1, for example, this is the equation of a line where a is 5 and b is 1, right? So this is the equation of a function, and this is what we're used to seeing. However, here we're going to start looking at things more and more where a function is really a linear combination of other functions, where we're going to call each function a basis function. So phi 1, phi 2, phi m. So over here, there are m functions, and the actual function is really just a combination of them, right? Our linear function is an example of this, where there are only two functions, this one and this one. Okay. So the way we can view this is that the first function is a times phi 1 and b times the second function, where the second function is just equal to 1. So whatever value you put in, it just gives you 1. And the first function, whatever value you put in, it just gives you x. Therefore, you can see this equation of a line is really a linear combination of two functions. Depending on how you pick a and b, you'll get a different line, but still a line regardless. So, so the key here is to start changing how you view functions. Instead of a single entity, you want to start thinking of them as components. You can break functions down into other functions like this. And then by adding up a combination of functions, right, you got the final function back. Let's name these components. Okay, so these functions that we use to form our final function, we're going to call those basis functions. Okay? Basis functions. So that's the set of these functions. Notice you have phi 1, phi 2, phi 3. So this is telling you the underscore is that it's a basis function. And these basis functions, they're the one that forms the building block of your final function. And we're going to call these constants at the front, a, b, the weights or the coefficients. So weights. So you can imagine how much of weight you put on each function as a weight, but they're also called coefficients. So they're the same. In this example, a line is really just a combination of two basis functions, phi 1, phi 2, right? And this is a line. The basis functions are important because depending on the basis functions that you pick, right, it basically tells you the type of functions you can construct, right? So if you use the basis functions for a line, then you'll be able to draw any possible line. But you're not going to be able to draw a parabola, for example, right? So in this particular example, we have three basis functions. 1, 2, 3. So these basis functions, where the phi 1 is x squared, phi 2 is x, phi 3 is 1. Now, if we use these basis functions, we plug this in, notice how this is the equation of a parabola. Therefore, using this equation, it allows us to generate any parabola, like here, here. See? So over here, right? This right here it came from this, where this is 0 and this is 0, and a is equal to 1. And that gives us the red line. And this right here is the equation of a line, right? So if you get rid of this and just have these two. So notice that even though this is the equation of a parabola, the equation of a line is still within it. If you get rid of this, that is essentially of a line. So if you just set a to equal to 0, you get a line back. So not only with this function, not only can you represent all the parabolas, you can also represent all the lines. Now over here is another example. This is green, the green line over here is another parabola, and over here is another line for purple, right? Okay, so the basis, remember these functions are called the basis functions. The basis tells us the space of possible functions, and the coefficient tells you the exact function. Like, take a second and think about that. The basis tells you the kind of functions, the space of possible functions you can have, and the coefficient tells you the exact function. Now, let's turn our attention back to the line. So this was the equation of a line. Okay? Now, if this is a line, this implies that we can split this equation into a dot product. So it's AB times this. Remember how this multiplies down, this multiply, which is equal to this. Okay? Now, we, instead of writing it this way or writing it this way, we like to represent this as what we call weights. So it's just a vector, right? So this whole vector is equal to W transpose. And this right here, where we combine all the bases, right? Instead of writing every single one of them, because you could have a long list of them, we just write one, which is phi. Okay? So phi represents this entire set of basis functions. And we're going to call this function, right, where if you plug x in, you get this whole vector out, as the feature map. Okay, feature map. Okay. Okay. So now, by knowing the basis, that's great. We know this, but we don't know the function until we know the coefficients as well. Okay? And this right here is the key insight. I mean, it sounds very obvious. If you want to know the function, obviously you need to know the basic functions and you need to know all the coefficients. Well, by knowing the basis functions, it tells you the type of functions you can construct. By knowing A and B, right? So for the line, this tells you it will be a line. By knowing A and B, it tells you exactly which line we're talking about. And this is a real key insight that you must know A and B in order for you to know which line or which function we're talking about. So once the basis function is defined, right, we've decided on a set of basis functions. These are the functions I want to use. Knowing the coefficient uniquely, and the key word here is uniquely, defines a function. So once you know which basis we're using, we can essentially forget about this. By knowing which A, B, C, D we're picking, this uniquely tells us which function we're talking about. Okay? So the basis function defines a space that spans all possible functions. This tells you all the possible functions you could have. The coefficients, these, tells you which function exactly we're talking about. So for the equation of a line here, the phi here tells us that f of x will always be a line, right? But a and b tells us which line exactly we're talking about. So this is really subtle change. It seems very subtle, but it's actually a really big conceptual difference, right? So the statement that the basis function defines a space of all possible functions. We're gonna go. I keep using the word space. You may not know what I mean. What I mean by space, but you can kind of imagine that by knowing the basis functions, it does tell you all the possible functions you could have, right? You could tell you all the possible. The coefficient uniquely identify the exact function. So the coefficient uniquely identify the exact function. Now, this is really, really powerful if you understand this concept and its implication. This is powerful because once we accept and agree on a set of basis functions, we can just forget about the basis functions. So once we know that these are the basis functions, right, we can agree on that. We simply don't need to talk about anymore. We just need to talk about A and B, right? By knowing A and B, we know which function because the basis functions has been agreed upon. So once we agree upon to use, for example, phi 1, phi 2, like equation of a line, right, we can communicate about functions using only coefficients, right? For example, instead of representing a function, so previously we would say this is a function of a line. Now we could equivalently understand which function I'm talking about by saying the function is equal to 3 and minus 2. Okay? Notice how it's 3 minus 2. That's A and B, A and B. So by communicating about just the coordinates, the weights or the coefficients, we know which function I'm talking about. And that this right here uniquely identifies a function. And this implies that an alternative way to interpret functions is a vector. Okay? So this is the conclusion that we can now look at functions instead of like this, right? We can now start picturing functions as a vector. 3 minus 2. So 3 minus 2, 3 minus 2 would be like a point here. So we can picture functions as a point in a space. Okay? This is very different way of thinking. Again, previously we think of functions this way. Now you can think of function as a point in space. So over here, we have three functions. These are all lines, right? So the blue one is right here. This is the blue line. And the blue line is 1 minus 2. So 1 minus 2. So this dot here, this point in space, like here we're picturing as a point in space, whereas over here is an actual line, and they are equivalent to each other. Okay, so we're instead of thinking of it as a line, we are now going to think of function as a point in space, right? So this one right here will be 1 0, right? So it will be this point. So the black line is going to be this point, 1 0. And the purple line is 3 minus 5, which is right here. So this right here is the purple line. So we have three functions of line here. So three lines here, and they equivalently can be thought of as three dots in this 2D space. Okay, so this is the key point, like that you can think of functions as our traditional functions, or you can think of functions as a point in space. And it doesn't have to be 2D, it could be 3D, 4D, 5D. It depends on how many basis functions you have, right? If you have phi 1 all the way to phi 100, then you're going to have 100 weights. So you'll be in a 100 dimension space. Okay? Functions as points. Okay? So given the example of a line, phi 1 and phi 2 essentially give us the axes of the 2D plane. You see, this is a 2D plane where this is phi 1 and this is phi 2, right? Some combination of phi 1, phi 2. And every single point in the plane is a distinct function, right? So I just showed you here, you have blue, green, and red. Blue, green, and red, right? The function as points in space, a function as lines or drawn out lines. And these two are equivalent way of thinking about functions. And this is why I keep saying that when you decide on the basis, you're essentially decide upon this space, right? You're deciding upon the space, which every single point within the space is a function. And if you pick two, right, it will be in a 2D plane. But had you picked three of them, then it's going to be a 3D space. And the points in here will be a function as well. Okay. So we call this 2D space. So this is a space of functions. So we can call a function space, a function class, hypothesis space. So these are the different names we're gonna call them. Later on, we're gonna call this we're gonna give it even another name called the RKHS. Okay, so it's you can just picture all these as the same thing for now, and that they're all the same thing, and it's just a space. It could be 1D, 2D, 3D, 4D, whatever D, and every single point in the space is defining a particular function. Okay, so the function space is essentially a space of functions, like representing all the possible functions contained within the space given the basis functions, right? Very important. You have to make sure you define the basis functions ahead of time and agreed upon. And then, once we agreed upon, then we can have this dual visualization of functions. And this is a very big perspective shift where viewing functions as a vector is really as a point, right? It's a very big shift because most of us are not really used to think of functions as points. If a function could be treated as a vector, most of what we learn from linear algebra now suddenly can be applied to functions. So for example, the concept of adding two functions. Previously, if you want to add two functions together, now, believe it or not, it is equivalent to adding two functions together. So this is a vector, right? So if you just essentially add two vectors together, right? Now, now you can this is a new function and it's equivalent to adding the two functions together. And another thing is, well, you can transform, right? If you multiply f by a matrix A, then you transform f to another vector, right? So one vector to another vector. And when you do that, this is a function transformation. And the idea of transforming functions now starts to make sense. Previously, we're also used to think of functions of f of x. And therefore, if we just say f, doesn't really make sense. However, now when we say f, it means it's a vector. Like you can think of it that f is really just a vector and a point. Okay? And this perspective shift allows us to view functions as object in its own right. So functions, previously you have to have some kind of input, but now you don't have to have input anymore. A function is simply a point, and the point can interact with the input. Okay? So without this perspective shift, you won't understand what f plus g means. Like if we have two functions and you're just adding them together, right? Previously, you're not going to understand what that means. Or f times some kind of a, which is the operator, and then you transform into g. Like this won't really make sense either. Okay? This perspective shift applies to machine learning problems. In machine learning, most of the time, we're looking for function f in space, right? So remember, in regression, we spend a lot of time working with regression. And the goal is to find this function, right? And then since we don't know the function, what we are doing is we assume that the function is a linear combination of other functions. And then we find the coefficient. So in machine learning, very often that's what we're doing. We're just finding a function that gives us a great prediction. Or in maximum likelihood, we're trying to find a function again, but it gives us a probability of events. So that's the difference. Okay, so hypothesis. Remember the different names to that I can define the function space. So I call it function space, all right? Function space, space, hypothesis space, hypothesis, as well as RKHS. So what does it mean when I call it a hypothesis space? Why is a hypothesis? Well, what's happening in machine learning? Let's say we have this data set, right? It's obviously should be a line, and this means that if we pick the hypothesis of a line, there are many different possible lines. This is a possible one. This is another one. This is another. They're essentially infinite possible lines, which you can pick, and 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 once as soon as we decide that it's a linear model, what we're implicitly forming is this 2D space. And this 2D space is the hypothesis we form, which the hypothesis is saying that the function, the true function, is somewhere within this space. Right? Therefore, this is the hypothesis space. We created this space saying that the function, the true function, is somewhere here. Right? So the green line is here, and obviously the green line would be a wrong solution. The red line would be the right solution. So it is correct that the red line is within the hypothesis space. So when we're trying to like do regression, for example, what you're doing is you're trying to guess. You're trying to guess the best functions that will form this. And the way when you pick all the basis functions, right, you are creating an hypothesis space, a space of all possible hypotheses that could fit this line. Okay, that's why we also call it a hypothesis space, because we're assuming that the best function is somewhere within this space. Okay? Now, just because we pick a hypothesis space, it doesn't mean it's right, right? Sometimes maybe our hypothesis space is 2D, so it's this gray area, it's just a plane. But our true function is really in a 3D space. So, for example, you might want to fit a polynomial function with a line, right? So, if the red line is the true line, and you're trying to use a line to fit it, no matter what line you can pick any possible line, it's not going to do a good job of representing this parabola because you just can't. A line can never be a parabola, right? So therefore, this is an example where the 2D space is a space of all possible lines, all possible lines. However, this 2D space of all possible lines is not enough when you're trying to represent a point in 3D space, right? So over here, this point is right here. It's in a 3D space, which requires three basis functions. So so when you have three basis functions in only using 2D space to try to represent 3D space, you're going to fail. And no matter how well you do, you're always going to have some kind of error. So this is the closest you can get to the solution. But this is a big error, right? So you're always going to have this error no matter what. So that's an example when you pick the hypothesis space, in this case 2D, and yet the true function resides in a different dimension, which implies that it's impossible for you to ever reach that point because P is not in the span, of this plane. Okay. And what we call this right here is called the residual error. Okay? So this is the example where the basis function does not span the solution. So this is the solution. Your basis functions cannot span it. Okay, so here's a specific example. You look at these dots. So these dots is the data, and the optimal solution is a parabola, right? So parabola would be the green. This is the optimal solution. However, it would pick the red because if you pick your bases only on a 2D plane, you can never ever get to the 3D point. Okay? So this is an actual example where I try to use a 2D space, a function space, to represent a point in the 3D space. Okay? Picking the correct hypothesis. Now, picking the correct hypothesis is really tricky. If we pick the hypothesis too big, if it's really, really big, then it's very tough. It's a big space to find one point, one dot, right? And it could take a long time to find that solution. And if we pick something that's too small, then even if you use the best solution, it's going to yield a significant amount of error. So, in general, what we do is we start with simpler ones and we kind of incrementally make it harder and harder to see if it's improving the results. Okay, so notice that for a line, we can make it to fit a parabola if we simply add a basis. So we start with something easy, right, with two basis functions, and then we can add more, right? By adding a third basis function, we can start expanding the space bigger and bigger. Okay, so now that I've convinced you, hopefully, that you can think of f as a vector. A function is you can think of as a vector. Now, what is the new way of thinking of f of x? Right? If f is a vector, what is f of x? Well, let's go back to how we got f in the first place. Remember how we got f, right? Well, f is essentially a linear combination of functions. And therefore, its f is equal to abc, right? Therefore, what does that mean? Well, this implies that f of x is equal to abc, which is the f, times the feature map. Okay? Remember, the feature map is a collection of all the basis functions. So this means that if we want to find f of x, we could all simply plug x into each basis functions, give us the feature map, and then do the dot product with the function. Okay, so which means we pass x into the feature map and do a dot product with f. Another way to write it is this: the inner product between phi of x and f. So this is what f of x means. If you know f is a point in space, right? So this is f. Now what you do is you find phi of x, which let's say is, I don't know, you plug x into phi 1 of x, phi 2 of x, phi 3 of x. Right? So now you have a vector and a vector, and you take the inner product. That is how you could find the result of f of x in this new perspective. Okay? Depending on how many basis functions, right? You don't want to write this, so we always write phi of x. Remember, it's very important to distinguish the two. When there's a number underneath, phi 1, phi 2, phi 3, we're talking about basis functions. When there aren't any, we're talking about feature map, where feature map is a collection of base. So this is a vector, whereas these just give you a number. So they're different. This give you a vector. These give you a number. So therefore, the conclusion is that the way we can think of the function how is that you pass x into feature map and then take the inner product with a vector f. Okay, so this has a very special name called the reproducing property. The reproducing property is essentially how you think of functions and inputs into the function and how you can evaluate that value. Okay, and once again, this right here is called a feature map. Again, do not confuse feature map with basis functions. Right? When you see numbers underneath, those are basis. Without number, that's a feature map. Okay. The visualization of reproducing property. Well, notice that after mapping x to phi of x, the dimension is equivalent to the dimension of f, right? Obviously, because there are 3 of them here and there are 3 of them here. So the dimension always matches. That's how you can always do a reproducing property. Okay. Now we're going to call the space of all original data. So this is the data. Let's say it's 2D, and therefore every single point is a potential data. So this whole space are where the data comes from. And we call this right here the data space. So this is the original data space. And then once we map through the feature map, so feature map is however many dimension. Here's 3 dimension. So you take a point here, you are mapping it to this space. All right, so this from point to a space. So this right here, after you pass it through the feature map, you're going to be in a 3D space. So because there are 3 of them, it could be 4D, but so you're going to be in this 3D space, and this data has a representation inside this function space, and the function itself also has a representation. So the 2 points in here are both in 3D, and you can take the inner product between the two. Okay, so visually, what's happening is the function is in the function space, or we call it also the hypothesis space or the RKHS. So the function is in this space, and what's happening is you map the data into another point in the same space, and once they're in the same space, you can take the inner product between them because they have the same dimension, and that's how you can visualize what's happening when you are evaluating a function. Okay, the function exists in a function space. You take a data point, map it to this space so that they have the same dimension. You take the inner product, and that is equal to f of x. Okay. Another way to visualize it is this is the function space, and every single point from the data space could be mapped to a distinct point. So this will go here, this will go here. These are all different points in function space, depending on what you put in. Okay? All right, take a moment and clarify in your head the difference between them. Okay, so this is phi and x. Yeah, I keep going back to this. Phi 1, phi 2, those are bases. And the one without the number, that is the feature map. Okay? All right, you want to pause the video and see if you can consolidate these ideas by answering those questions. If you can easily answer these questions, hopefully, you will be essentially at a good position to understand what's happening. Okay? Now, spaces. I keep talking about spaces. The spaces are really important. Now, we did this before. Let's go over it one more time. A set is a collection of distinct elements. So this is a set of animals, set of flags, set of numbers, right? And then we represent set with a capital cursive letter. So this is a set. That's another set. There, that's yet another set. Now, a space is a set. Space is equal to set, but with some defined properties. So let's say we have a set of flags, right? If they're just a set, there are no properties defined. So how would you compute the addition of 2 flags? Well, if you don't know the property, you can't. But once we define a property, a set is now a space, and depending on how you define it, that particular space comes with associated definition. So this could mean the summation of the population of the 2 countries, for example. And I'm going to call this the Wu space. So Now that I have defined what the meaning within Wu space of flags are, you can start adding flags. You can subtract flags. You can multiply them because we may created this definition. So within Wu space, a set of flags makes sense when you add, subtract, divide them, whatever, right? Now, anyone can make up a space, and essentially, you just define the set of properties that will work within the space and normally name it after yourself. Okay? Knowing the space you're working tells you the operations you're allowed to perform, right? Like my operation on additional flags, right? Because you're in Wu space, you now know that elements in the set, the flags, can be added together or subtracted. Now, if you're not in a Wu space, then that's not going to work. Okay, so in mathematics, we have lots of spaces. Vector space, right? When you deal with vectors, you're assuming it's in a vector space, and therefore the additions, all that stuff work. Metric space, norm space, Banach space, Hilbert space, reproducing kernel Hilbert space. So spaces inside other spaces implies that all the properties of larger space is inherited. Therefore, RKHS inherits all the Hilbert space properties, all the Banach space properties, all the norm space properties, all the vector, all the metric space. So each one of these space has certain operations defined. So vector space, vector addition, subtraction. Norm space, the concept of norms now is defined. Or Banach space, right? Or Hilbert space, the concept Hilbert space is the concept of inner product is defined. And RKHS therefore has all these spaces defined. So the reproducing kernel Hilbert space, also known as RKHS, is a very specific space that essentially has the property of all of these things, and it's defined. Now, a metric space is a space where the concept of a metric is defined. A vector space is a concept where vectors are defined. And a complete space is a space where concept of completeness is defined. And this pattern continues. A norm space is a concept where a norm is defined. Or inner product space is a space where the concept of inner product. So following this pattern, if this says it's a reproducing kernel, Hilbert space. So this is saying that this space is a Hilbert space. Therefore, all the inner products are defined. Therefore, what's special must be the reproducing part. The fact that reproducing kernels are defined in this space is what makes this special. Okay? So based on this pattern, we can essentially guess the definition of reproducing kernel Hilbert space. That reproducing kernel Hilbert space is simply a Hilbert space where the concept of reproducing kernel is defined. Now, this is not the original definition, and I don't claim to be even a good definition, but this is actually a very useful definition to understand what a reproducing kernel Hilbert space is. It's just a space where the reproducing kernel is defined, and it's good enough for now. Now, therefore, if you know what a reproducing kernel is, then you know what the space is all about. Okay? So, to define a reproducing kernel, there are two stages. First, you need to understand what is a kernel. And second, what is a reproducing kernel? So, a kernel and a reproducing kernel are slightly different. So, to define a kernel, remember our data came from a data space. And we're going to call that space X. So, that's the data space. And the feature map is defined phi. And the space of functions, we're going to call RKHS, and we're going to represent that as H. So this is the data, and this is the function space. So we're mapping it, the data to function space through the feature map. Okay. So let me draw this out. Here's the data space, and this is the function space. and this is phi. So assuming this exists, let's start from there. Then a kernel or a kernel function, right? A kernel function is a function that basically takes two values. Remember, function very often take one value, but a kernel function is a function that takes two values. And the way you evaluate this function is you take the first value and map it to the RKHS or the function space, and you take the inner product with the second one. So this is the definition of a kernel. You essentially have 2 points, 1, 2. You map them both here. And once you have the 2 points here, you take the inner product, and that is equal to the result. Okay? So this is the function. Now, a kernel function, I mean, you can read the definition. In simpler, what I gave you is a simpler way of understanding it. A kernel function takes 2 points from the data space, 2 points, and then map it as 2 points in the function space through phis. So once you pass it in the feature map, you have 2 points. And then you take the inner product of those 2 points in the function space. And that is what a kernel function does, right? So if you know that a kernel function exists, therefore it kind of comes along with the fact that a data space, a function space, and a feature map must already be defined. Okay? So now that was the definition of a kernel. So kernel, one more time, a kernel or kernel function is a function that takes 2 points. That's what this says. It's a function that takes 2 points from the data space and outputs a number. And the way it outputs a number is through the inner product. Okay, so that is a kernel. What about a reproducing kernel? Well, a reproducing kernel, so this was the definition of a kernel. And from the definition of the kernel, it tells us that if we just pass 1 point in, right, remember this is the data space. Therefore, if we just pass 1 point in, this is also equivalent to 1 point inside RKHS. Right? That's what this. So you can. This is what this notation means. You just pass one value, which pass that one value to RKHS. So that is a kernel. Now, a reproducing kernel is just a kernel. A reproduce is a kernel that satisfies two additional criteria. So criteria number one is that every single point in X, and you want to map it. You want to map it to RKHS. Every single point here is a point in here as well. So that's condition one. Okay? For all X, you must be able to map it here. And the second condition is that reproducing kernel must have the reproducing property, which means that if you have a function, then the function must follow the reproducing property. So this means that when you're within RKHS, you can think of functions as the way we have been thinking, with the way I introduced today. That function is a point in space, and the way you evaluate a function is through the inner product. So the reason why you can do all these is because we are within a reproducing kernel Hilbert space. Okay? Now, reproducing kernel Hilbert space is a space where a reproducing kernel is defined. So now that we know what a kernel function is, and we know what a reproducing kernel function is, then a reproducing kernel Hilbert space is a space where this concept is defined. Right? By mere definition of reproducing kernels in this space, then these concepts are definitely defined. Right? Once you know that we're in a reproducing kernel Hilbert space, then we know functions are defined this way. We know feature maps exist. We know that what a function space is, data spaces. We know what a kernel function and a reproducing kernel. So all these concepts are automatically defined if we are talking about reproducing kernel Hilbert space. Okay? Now, how do we use reproducing kernels? Well, there are three components to a reproducing kernel, or two components. First is that you can essentially take the inner product of these values inside RKHS. Or you can think of it this way. This is the reproducing property. Now, you want to follow this logic very carefully. Okay, if we put one value instead of two into a kernel, so we just put one of them, then if we put one of them, that's only mapping this one to the RKHS. So we got a point. If you only map one, here's the data space, here's RKHS. If you only put one inside the kernel, we're mapping it into this point. Okay, so that's what this means. And phi of x is a point in a function space of H. Okay, so once we map it here, this is a point in the function space. So you can view this as a function, or you can view this as a data in the function space. You can view it both ways. Therefore, this right here, by mapping one, you are defining a distinct function. Okay, so this is the logic jump that you need to think about. So you can think of mapping this point here as mapping the data into the function space. But every single point in the function space is a function. So by putting a value inside a kernel function, you are defining a function, right? Depending on what you're putting here, you're defining a different dot inside the function space. So you are defining a distinct function. Therefore, plugging in different numbers, right, into the kernel function, you're picking a function inside a function space. Depending on what you're putting here, you're picking a function inside the function space. Now, if you were to put two values in, it implies that you're picking the function with one of them and evaluating them with another. So this right here is a function, right? So this is equivalent to picking a function, f of xi, and then evaluating xj. So this logic is a really big jump, which you have to think about. But this right here, when you have two variables, you're picking a function and you're evaluating it. Okay. Now, so that's why a kernel function that has two inputs is really special, because you can view it as using one of them to pick the function and another one to evaluate at a particular point. Okay. For example, let's say we have a linear kernel, right? So phi1, phi2 is equal to this. Therefore, the feature map is x and 1. Now, if we have a kernel and we plug in the value of 1, okay? Now, when we plug this in, it's equal to phi1. And phi1, this is a function. And therefore, by plugging this in, we're saying that we're defining a specific function, and then we will put some value into this function by controlling this value here. Okay. Now, this logic is, you need to understand that you want to pause the video and you want to understand this logic before you move on. This lecture is a very foundational understanding, and if you don't understand these, then you're going to have a lot of trouble going ahead. Okay? All right, so a kernel function is a function and it returns a value. However, a kernel matrix is when you have n samples and you're doing this for every combination. So for the first sample, you're putting the first sample. For the first sample, you're putting the second, right? For the second sample, you're putting the first. Second, putting the second. So if you have n samples, the kernel matrix is a combination of every single sample. right? So this is KXI. So kernel matrix is K. This is K11, K12, K13, all the way K1n, right? So it's an entire n by n matrix. So that's the definition of a kernel matrix. Now, we would like to define the feature map as a phi matrix. So the feature map, right? So remember, this is a feature map, not a basis. So what's happening is you're passing every single sample out of n samples into the feature map. And this right here is the feature map matrix. So we like to represent this as capital phi, where every single sample is in there. And you can imagine that phi times phi transpose will be this times this, this times this, this times this. And this right here is equivalent to this here. So phi times phi transpose is equivalent to the kernel matrix. And if we're talking about x, sometimes we add an x here. Okay, so the kernel matrix and the phi is, you need to basically sort these out. All right, so this is the lecture. You need to pause and really, like, this is not a lecture you can just watch and absorb immediately. You need to think about it. You need to go through these questions, like go through these questions yourself, and then go through these questions so that you can start consolidating this knowledge. There's a lot of notation and there's a lot of conceptual novelty that you have to grasp. So make sure you know the kernel matrix. This in the end we end up dealing with kernel matrix the most. So these notations, like, I think it gets really confusing because you have phi I, right? Phi, and this is a like 1 phi 2. This is a basis, and then you have just phi of x, and this is a feature map. And then you have the capital phi. And these three things, how one evolves to another, is what takes the most time to understand. And it took me, like, if you don't understand it for initially, it's just because you haven't gone through the reps. You need to go through this over and over again. And then once it clicks, a lot of things will start making sense. Okay, so pause the video, make sure you go through these questions, and I will see you in the next lecture.